Hello. I'm going to skip the second order modeling set. We talked a lot about that on videos. And for the review, I'm going to move on to series solutions. So in this little review mini lecture, I'm going to talk about finding the series solution to dy dx is minus 3 times y minus 20, that same ODE we've been talking about. This is a first order, and it's non-homogeneous, so it's a little bit different from most of the ones we've done, but it has the same, it's the same technique, really. All right, so let's start by writing this in standard form. We've done this before. Dy dx plus 3y is equal to 60. So it's linear, non-homogeneous. It has constant coefficients. So in this case, it's kind of silly to be using a series solution, but right, that's what we're doing on the review. We're doing it lots of different ways, okay? And we're looking for a solution y as sum from n equals 0 to infinity, cn x to the n, so that's c0 plus c1x plus c2x squared plus dot, dot, dot. All right. Actually, while we're here, let's do the derivatives. The derivative is y prime is sum from n equals 0 to infinity. Okay. Cn times n times x to the n minus 1. And oops, actually, n equals 0 doesn't work. We start with n equals 1, right? Because this is equal to c1 plus 2c2x plus c3x squared plus dot, dot, dot. In fact, another way to write this y prime is sum from n equals 0 to infinity, c times sub n plus 1, n plus 1, x to the n. And then I get the same series from both of these. This one comes from when n is 0. When n equals 0, I get c sub 1 times x to the 0, which is 1. When n is 1, I get c sub 2 times x to the 1. When n is 3, I get c2. When n is 2, I get c3 times x squared. I get them all the same. Okay, so let's just plug this form and that form into here. So we get sum from n equals 0 to infinity, cn plus 1 times n plus 1 x to the n plus 3 times sum from n equals 0 to infinity, cn x to the n is 60. Okay? All right, I'm going to do this. So I can combine these into a single sum. Okay, I have common factors of x to the n in the two sums, so I can combine them. I get c sub n plus 1 times n plus 1 plus 3cn, and that gives us that. So gives us the same sum. Now that's 60. Now 60 is also 60 plus 0 times x plus 0 times x squared plus 0 times x cubed plus dot, 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 right? So I want this function of x to be that function of x. That function of x looks like a constant, but it's a constant plus 0 times x plus 0 times x squared. So I get, for the constant term on both of these sides, I get, when n is 0, I get c1 plus 3c0 is 60. And then for the rest of them, I get c sub n plus 1 times n plus 1 plus 3 C sub n, that equals 0. For n equals 1, all right, 2, 3, dot, dot, dot. The coefficient of x to the n when n is 1, 2, 3, etc. are all 0. Okay? And I like to solve these before I box it as the recurrence relation. I like to solve for the highest coefficient. I get C1 is 60 minus 3C0. In fact, that's, by the way, that's minus 3 times C0 minus 20, isn't it? Okay, okay, good. And then I get Cn plus 1 is minus 3Cn over n plus 1. Good. For n is 1, 2, 3, dot, dot, dot. Okay, so I'm going to box this. Let's use some of my orange here. So this is the recurrence relation. Okay. And I think I can erase everything except maybe that, but I think I'll erase that too to get more things. We remember that part. So everything is gone except for the recurrence relation. That was step 1. Step 2, solve the recurrence relation. Okay. Okay, and you notice that the recurrence relation doesn't tell me at all what C0 is. C0 is totally arbitrary. It starts with C1, and that's because this is a first order ODE. If I had a second order ODE, then the recurrence relation would not tell me what C0 and C1 are. They're arbitrary. And then the recurrence relation would tell me what C2, C3 is, etc. Okay? But the other thing is it doesn't tell it to you, it doesn't give it to you, on a platter. It gives you this kind of coded form what the Cn is, right? I can't look at that and tell you what C sub 385 is, right? Oh, because I need 384, C 384, etc. So to, quote, solve recurrence relation is, well, sometimes you just get a few terms and that's enough, or sometimes you can actually find a formula for Cn for any n. And then we'll probably try to do that here. Okay, so let's solve it. So solve it, we have C0 is arbitrary. And note that y of 0 is C0. Okay. So in other words, this I can get a series solution for any initial condition. Okay, and then what is C1 is minus 3 times C0 minus 20. What is C2? That's when n is 1 here. C2 is minus 3 times C1 over 2. So that's minus 3 over 2 times C1, which is minus 3 times C0 minus 20. So let's write this in a nice form. It's going to be minus 3 squared over 2 times C0 minus 20. Okay, and then what is C3 is minus 3 over 3 times C2. I don't want to cancel those because I want to try to figure out what the general form looks like. So this is minus 3 over 3 times minus 3 squared over 2 times C0 minus 20. And And what is that? Well, that means there's 3 factors of minus 3 cubed over 3 times 2 times C0 minus 20. What is C4? Minus 3 over 4 times C3. And that is minus 3 over 4 times minus 3 cubed over 3 times 2 times C0 minus 20. That is equal to minus 3 all to the 4th over 4 times 3 times 2 times C0 minus 20. Right? So let's this is also 4 factorial, right? So, right? So, in fact, what we've said is that C0 is arbitrary. Cn is minus 3 to the n over n factorial times C0 minus 20. Like it works for C, it's easier to see with things like 4. When C sub 4 is minus 3 to the 4 over 4 factorial C0 minus 20. C2 is minus 3 squared over 2 factorial, which is 2 C0 minus 20. And it even works for C1, right? This works for n is 1, 2, 3, dot, dot, dot. Okay. Okay. Does it work for C0? Minus 3 to the 0 is 1. 0 factorial is 1. Okay, C0 is C0 minus 20. I don't think it works. It just works for n equals 1. Okay? All right. So what do we got here? Let's see if we can put them all together. So we get that y is C0 plus sum from n is 1 to infinity minus 3 to the n over n factorial times x times C0 minus 20 times x to the n. Okay? All right, so let's think about this. This is going to be 20 plus C0 minus 20. That's another way of writing 20. Plus, let's write this from n equals 1 to infinity minus 3 to the, let's combine this. Minus 3 to the n times x to the n is minus 3x to the n over n factorial, right? Oh, but now I can combine this with that term, and I get 20, plus I can do sum from n equals 0 to infinity. Oops, I forgot the C0 minus 20 here. Okay. Okay. All right. So this thing here is just e to the 3x. This says that y is the 20 plus e to the minus 3x times C0 minus 20. Okay, so our final, maybe not final, at least our next method of deriving the solution, we'd call that thing C-twiddle before times. Okay, it's an arbitrary constant, but actually this is a little bit better than just saying C-twiddle. This is the initial, this gives you the solution with the initial condition y of 0 is C1. All right, so let's Yeah, a little bit harder than the others, especially I think solving by inspection is probably easier than this, but at least it demonstrates the method. Okay, bye.